Good morning, ladies and gentlemen, and welcome to the video for Calc Review 19. This will be the last Calc Review worksheet that I give you. You might have seen the email I sent today. Since the AP is just a few days away, we will be looking at mock exam problems for the upcoming AP from now on. Okay, so anyway, that's just a little look ahead. For today, I'm going to go over this problem. It was a frequently asked question on the question stream, and I'm also going to cover parts B and D here because they were also frequently asked. If you do want me to go over parts A or C, please let me know, or just drop by SGI real quick and we can go over those very quickly. All right, let's start with this problem here, the multiple choice. So this is, the key to this problem is understanding the language that we are given. So first off, we're told that the rate of change of volume of the oil tank, of oil in a tank with respect to time. So they're saying that there's some rate of change of volume of oil in a tank with respect to time, and they're saying that that is inversely proportional to the square root of volume. So this is basically describing a relationship which we can convert into mathematical symbols using an equation. So the left side of the equation is referring to the rate of change of volume with respect to time, aka dV dt. We are then told that that quantity is inversely proportional to the square root of V. The term inversely proportional means that this value dV dt is equal to the product of some constant times 1 over square root of V. Inversely proportional means we are taking the reciprocal of the square root of V, or 1 over square root of V. If we were told that dV dt was directly proportional, or just simply proportional to the square root of V, then the equation would read dV dt is equal to K times radical V. All right, so it's important to know the difference between those two phrases. It then goes on to give us two different initial conditions. So if the tank is empty at time 0, and also if V equals 9 at T2, then find the equation which describes the relationship between T and V. All right, so basically we need to solve this differential equation. Remember, the solution to differential equations are equations themselves. So we need to find the equation whose derivative basically is K over radical V. And the solution must also satisfy these initial conditions. All right, so first step is to separate the variables. And integrate. All right, left side, you have V to the 3 halves times 2/3. Right side, you have KT plus C. All right, now at this point, we can go ahead and use our initial conditions. I'm going to use the first one, which says if the tank is empty at time t equals 0. Another way of saying that is when t equals 0, V equals 0. So let's use that. So I'm using this initial piece of information. So I have 2/3 times 0 to the 3 halves is equal to K times 0 plus C. And this implies that C equals 0. Okay, that's nice. I'm going to just kind of draw a line down here to kind of separate. So where are we at now? We now know that our equation is 2/3 times V to the 3 halves is equal to KT. I no longer need to write plus C because we just found out that C equals 0. The next condition that must be satisfied is that V equals 9 when T equals 2. So let's plug that condition in. So I have t equals 2, v equals 9. 2/3 times 9 to the 3 halves. I'm going to rewrite this as square root of 9 cubed. It's just an easier way of thinking about it and evaluating it, especially if you didn't have a calculator. And that should equal k times 2. So the left side, radical 9 is 3. 3 cubed is 27. I then have a 3 in the denominator. So 27 divided by 3 brings me right back to 9. So I have 18 on the left side, 2k on the right side. This, of course, implies, running out of space, so this implies that k is equal to 9. All right, and so now let's write our final answer. We have 2/3 times v to the 3 halves is equal to 9t. Going up to the multiple choice options, I don't see anything that looks exactly like my current answer, so I'm going to have to manipulate some things. I do see that C and D have a v to the 3 halves on the left side, so let's see if I can just isolate my v to the 3 halves. So I'm going to multiply by 3 and divide by 2, and that's going to lead to v to the 3 halves is equal to 27t over 2, and that looks like choice D. Yeah, 27t over 2. All right, awesome. So there you go. Choice D. All right, let's move on to the next problem. We have a differential equation. Remember what a differential equation tells us. It basically tells us the slope of the curve at any point x comma y. So that's why part A is kind of important. It sort of grounds you into the understanding of what we are given. We're given a slope formula, basically. So I can choose any point on the plane, plug in those coordinates into dy dx, and I know that that will be the slope of the tangent line of whatever curve goes through that point that has this differential equation as a solution. Or basically whose derivative is equal to this differential equation. All right, so that's what we're given. We're given a slope generating function, basically, or a slope generating expression. Part B asks us, though, to find the second derivative. Remember, the second derivative is basically like a concavity generating expression or function. So the second derivative is always going to, or typically going to be followed by some question about concavity. All right, so in this case, we're asked to find the second derivative, and then we're asked to describe the region such that all the solution curves are concave up. All right, so let's start with just finding the second derivative, and then we'll get into the whole concave up part. So dy dx is equal to 1/2 x plus y minus 1. All right, good. All right, now to differentiate, I'm going to apply d dx, the operation, the derivative operation, to both sides. Right, the left side, we just end up with d squared y over dx squared. On the right side, when I differentiate 1/2 x with respect to x, I get 1/2. When I differentiate y with respect to x, I get dy dx, because y is some implied function of x. And when I differentiate the constant -1 with respect to x, I get 0. All right, so this is an expression for the second derivative, but of course we want our answer to be in terms of just y and x, not dy dx. So this dy dx, I'm actually just going to replace it with this entire expression here. All right, so d squared y over dx squared is equal to 1/2 plus 1/2 x plus y minus 1. This should be in parentheses technically, but since we're adding the two terms together, the parentheses don't really come into play here. I'm going to just combine like terms. D squared y over dx squared is equal to 1/2 x plus y minus 1/2. All right, so that's the second derivative. Now, that's not the entire, we're not done yet with part B. Part B goes on to say, so we found the second derivative, check. Describe the region in the xy plane in which all solution curves to the differential equation are concave up. Concave up means we need to find when is d squared y over dx squared greater than 0. That's when the solution curves will be concave up. So I'm basically going to take my second derivative expression and set it so that it must be greater than 0. And what I'll do here is I'm going to solve for one of my variables. I'll solve for y. And so the second derivative is greater than 0 when y is greater than negative 1/2 x plus 1/2. So your solution or your answer can be written in the following way. Solution curves will be concave up for all points above the line y equals negative 1/2 x plus 1/2. All right, and that is the answer to the question. Again, the question says for you to describe the region in the xy plane in which all solution curves to the differential equation are concave up. Well, what we've done is we basically found an inequality that tells us, well, whenever there's a y value that's greater than negative 1/2 x plus 1/2, then the curve, the second derivative will be positive, and therefore the solution curve will be concave up. So just explaining or describing that inequality in words looks something like this. Solution curves will be concave up for all points that are above the line y equals negative 1/2 x plus 1/2. All right, let's go on to part D. Just give me one moment. All right, welcome back. So part D asks, find the values of the constants m and b for which y equals mx plus b is a solution to the differential equation. All right, this is a tricky problem because it sort of presents a situation that we're really not used to. When we hear that so-and-so is a solution to an equation, we're thinking of a number that we plug into an equation, or let's say a set of coordinates that we plug into an equation, and those coordinates satisfy the equation, right? That's what we usually think of when we are talking about a solution to an equation. But the thing is, as I discussed earlier, solutions to differential equations are the original functions or the original equations or curves. And so the concept is the same though. What we can do is we can take our solution, which is y equals mx plus b, plug it into the differential equation, and that equation should be satisfied. All right, so that's the idea. Let's go ahead and execute. So let me just get the differential equation, 1/2 x. All right. Looks like I was going to start down there. All right, dy dx equals 1/2 x plus y minus 1. I just want to double check that this is correct. 1/2 x plus y minus 1. Okay, awesome. So part D tells us that y equals mx plus b is a solution to the above equation. Okay, well, what does that mean? Well, basically, remember a differential equation, that left side, that dy dx, that is a slope expression. So the differential equation tells us the slope of our solution curve at any given point along that solution curve. Now, it turns out that our solution curve is an equation y equals mx plus b. Well, that's a line. So our solution curve is simply some line. Well, if that's our solution curve, then it's obvious that y prime, or in other words, dy dx, is equal to m, right? The slope at any point along this solution curve is going to be m. That's one nice thing about lines, is their slopes are constant. All right, so the fact that we have a linear solution curve means that dy dx is equal to that m term in the linear equation. So we can use that fact to say that m equals 1/2 x plus y minus 1, right? Similarly, instead of writing y here, I know that y is equal to mx plus b. So I can write this as m equals 1/2 x plus mx plus b minus 1. And now I'm going to combine like terms. So I'm going to combine the x terms together, and I'm going to put all the constants together. So I have m equals 1/2 plus m times x plus b minus 1. Okay, now, a lot of the questions in the question stream were basically asking, why can we plug like 0 in for x? Why can we plug 1 in for x? Well, let's think about this. The equation is a line. Well, what do we know about lines? We know that lines are continuous on negative infinity to infinity, right? So basically, I can choose any x value from negative infinity to infinity, and I know that my function will be defined for that x value. Not only that, lines are not only continuous, but also differentiable. So not only is the line continuous, but so is the derivative continuous. The point I'm trying to make by saying this is I can choose any value x and plug it into my equation, because x is defined, or the function and its derivative is defined for all values of x. So basically, I'm going to choose x values that are convenient for solving for m and for solving for b. The first one is 0. 0 is a very convenient value to plug in. Why? Because it will get rid of this entire first term here, which will allow me to get an expression of b. So let's let x equals 0. We have m equals 1/2 plus m times 0 plus b minus 1. Of course, this term is gone, and I'm left with m is equal to b minus 1. Or in other words, I mean equivalently, you can say that b is equal to m plus 1. Cool. I mean, I don't have an actual numerical value for either of these terms yet, but I do have a direct relationship between them, which is nice. All right, let's now try to move forward, and let's say let x equal 1. All right, so where are we now? We have m equals 1/2 plus m times 1 plus b minus 1. But instead of b, I'm going to plug in m plus 1. So I have m plus 1 minus 1. Right? I just put this guy in here instead of b. All right, now let's simplify. You can see at this point the only unknown value is m. So I'm going to go ahead and solve for m. M equals 1/2 plus m plus m plus 1 minus 1 is just m. So of course we have m equals 1/2 plus 2m. And this ends up giving us that m is equal to negative 1/2. All right, so that's the value for m. I don't have the value for b yet, but I do have this very nice relationship between b and m. So that means b is equal to negative 1/2 plus 1. And in other words, b is equal to positive 1/2. And there we have it. So that would be the final answer for part D. D, very tricky question. It does require some a pretty good understanding of really what's going on when we are given a differential equation. The key is just understand a differential equation just simply tells us the slope of the tangent line at any point along the solution curve. All right, ladies and gentlemen, that is all for today. I hope this made sense. If you have any questions, do not hesitate to drop by SGI or just email me. All right.